Hey, what's up, guys? What's up? Okay, and so today I want to talk about another NP complete reduction. It's called three coloring. Okay, okay. So I think previously we know we got some NP complete reduction. So the previous one that I did is very simple. That you just break up set, so you can prove that circuit set. Sorry, you can prove that three set is NP complete. By proving the sets actually can be polynomial reduction to three sets by just breaking the large. If you have the three variables, more than three variable in the clause, then you can break up. Okay, and I also proved like the linear. I proved that the linear integer programming, so LIP, is also NP complete by reducing by proving that if you can solve LIP, then you can solve so-called vertex cover. Okay. Okay, so these are a very simple idea, but now we need to contain something. We need to break everything into pieces and prove prove a lot of problem which is NP complete. Okay, so now some of them are very simple. The vertex cover is actually so if you take one can easily prove that the vertex cover is actually a complement of the independent set. So in the independent set still, NP complete if you know vertex cover. And one can prove the independent set of NP complete using the so-called three color, which is 3COL, which is the topic today. And so in this video, I want to prove that actually one can prove that three sets can be polynomial time reduction to three color. Okay, and also four color. Okay, I'll keep going. Okay, so these are all NP complete. So before I start, let me just give a rigorous definition. So K coloring means that somebody give you a graph G and a graph G, which is a vertex and edge, and so when I say that G is a K colorable, okay, K colorable means that so you can use K colors to color G, okay, to color G, and there is a condition, right? So you cover the vertices such that no common colors. If there's edge, U and V, connecting them, then the UV must have different color. Okay, so for example, let me just using many colors. For example, let's prove a triangle, right? So if you have a triangle, let's prove if you have a triangle here, then this graph, this triangle G is three colorable because I can create red here, and I can use, let's say, green here, and I can use blue here. Okay, and if there's an edge connecting, then the adjacent vertices must have different colors. Okay. Okay, so trivial. So if G has n vertices, then G is uncolorable. Okay, so obviously that G is uncolorable, right? So G may not be a -1 colorable or a -2 colorable. Okay, so one can so there's a number called the chromatic number. Chromatic number should define to be the minimum colorable. So minimum K. Okay, such that G is K colorable. Okay, so for example, for this triangle, that you cannot use two color because if I use this, because they are connected to each other, right? So if you put like two color, then it can not be two colorable, right? So the chromatic number is 3. Okay, so The problem in the computer science is that somebody so given as a G, and then you want to output one, your output Euler G is 3 color. Okay, so this problem is a decision problem called 3COL. Okay, so the theorem, which is I'm going to prove this, is 3COL is NP complete. Okay, and then let me just quickly notice. If you want to ask the two colorable whether the graph is two colorable, this is essentially the same as whether this graph is bipartite, which you can solve this by BFS, so breadth first search. So this is a polynomial time. Basically, it's all order of n plus n, where m is a number of edges. Okay, so in order to prove 3 colorable is NP complete, this is the hard part. We need to start from set. Okay, so this is the difficult part. Okay, so we want to prove this. This is the most difficult part. Okay, in this proof. Okay, so we need to build out in the computer science. This is called gadget. Okay, so idea is that in the 3 sets, right? So we have variables. We have x1, x2, up to xn, and maybe x1 bar, x2 bar, xn bar is called the literal. And we also have the clauses, right? So clauses. So clauses is that for example, let's say this. Right, this is clauses. Okay, so we need to somehow like build something which so somebody give you a phi which is in a 3 set, and then we hope to compute such that G phi, which is another graph. If phi is satisfiable, then G phi is 3 colorable. If phi is not satisfiable, then G phi is not 3 colorable. Okay, this is our goal. Okay, in order to do this, we need to do something non-trivial. Actually very non-trivial. It's not difficult but interesting. Okay, so idea is that the first for variables, let's say okay, so in the beginning, let me just create. We need to create something very looks very weird, called the truth table color. So let's create 3 colors. One is F. F is a color. Okay, so you can view as if F is red, and you can also create a color called green. Let's call it true, and create another color which is blue. Okay, and we connect them. Okay, once I connect, then this means that these are 3 different colors, and for each variables, I need to connect them. So, for example, if I choose, because for let's say right, this is so for each variable, this B is called basis, which we didn't assign, right? But for each variable, then either be true or F, right? So this basis should contain every edges, every variable. Okay, so this is the variable gadget. So this B looks like this. Okay, so this is the variable gadget. Okay, and for each x1 and x1 bar cannot be the same color, right? Either true or false. So I should connect them. Okay. Okay, and just keep going. For example, this is x4. It is x4 bar. Okay, so this diagram will force xi is either true or false, either T or F. And also xi bar must be different from xi. So if xi is F, then this is F, this is B, right? This can only use T. So we have 3 colors. I got T, F, B. So I view the true and false and the base as 3 colors. So if xi and xi, so if xi is false, then xi bar must be true. Okay, so this is a trivial variable gadgets. Just realize these simple things by each Ti, xi, or it must be T or F. Okay. Okay, and now here is a so-called OR gadget. Okay, so this is a simple difficult word. So before we start, let's play something stupid. Okay, so let's prove the ABC case. So this is our final results, right? Because we need to do like 3 sets, so we like solve these 3 clauses. Okay, so let's plug like ABC, and some people can come up with this beautiful diagram, which is solve our problem. So this diagram look like this. Okay, connected with B and T and F. Okay, so my claim is that this graph is recoverable if either one of if A or B or C is true. Okay, so if I want to prove that if A or B or C is true, then this graph is recoverable. Okay, proof is not difficult. So let's say BFT, let's solve some example. Let's say this is BTF, right? So this guy connected must be T, and okay, so let me see. I guess I miss. Okay, so sorry, I miss one line. Okay, so it's here. Okay, so if this is T, right? So these two must be different, right? Because this is triangle, right? So let's assume this is B, this is F, right? So if this is B, this is F, then C can be F or T. Sorry, C can be F or B. Okay, but let's put B here. Okay, so make it so C cannot choose B, right? So in this case, C must be T, because this is F, so C must be T. Okay, so now C is T, right? So this guy should be recoverable. So let's simply check it whether I can get for A and B, right? So if this is B, then this can be T or F, right? This can be T or F. Let's assume this is T, so let's assume this is T. Okay, so either this can be B or F, right? If this is B, then this guy cannot be B, right? Can be T, and if this is F, then this is B, right? This guy can be T. Sorry, this can be F, right? Because these are B, 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 so A can be T or F. So okay, so in this case, we prove that if we prove that ABC, if T, T, T is okay, so T, T, T is recoverable, and F, T, T is recoverable. Okay, if we exchange this, we get F and B, which is the reverse, right? So in this case, B can be T or F, and at least A must be T, right? So we prove that TFT is also recoverable. Okay, now we exchange our situation. Okay, so let's assume this guy is F. Okay, so let's exchange this to be F. Don't worry, it's not difficult. So let's assume that this is F. Okay, so if this is F, then what is this? This can be B or T. If this is T, then B can be F. Okay, if this is B, then this BB, right? So I get T and F. Okay, so I guess I get the same thing, right? Oh, sorry, you can get the T, you get the TFT and the FFT. Okay. Okay. So in this case, that you can see that you already get this, right? So if C is T, then you see that whatever you choose for MB always give you the recoverable graph. Okay. So this guy is always recoverable. Okay. So let's do this. So so I already proved these 4 results. Give you the same will make these graphs recoverable. So let's forget about this. And change our assumption, right? Let's change these 2. And I assume this is F, this is B. Okay, if this is B, then C can be F, right? C can be F, because I already consider C to be T, so let's assume C is F. Okay. If this is F, then this can be 3 of them. They can have 3 choice. Right? If this is F, then in order for, let's say, right? So let's say this is T. Let's say this is T, right? And let's assume that this is F and B. Okay. So if this is F, and B, this A can be F and T, right? But now this two of B, right? So B must be T. Okay, so you can see in this case, then B must be T. Okay, and if I exchange this to be B and F, so in this case, I can generate FT, F, and TTF. Okay, if I change this to be B and F, then this guy can be T. Sorry, if I change this to be F, then this guy can be what? Okay, sorry. Oh, sorry, I'm stupid. Sorry. I'm stupid. Ooh. Easy to confuse, right? So if this is F and T, let's say this is B and F, then in this case, BB, right? So this can be F and T, but this guy must be T, right? So I generate FTF and TTF. Okay. If I exchange this to be F and this to be B, then this guy can be TF, but this guy must be T. So I can generate TTF and the TFT, right? So the same thing, but I get TFT. Okay, so I already generate all the 7 cases. Okay, and then you can easily prove by yourself that if you choose ABC to be F, then this graph is not 3-color. Okay, so who should prove that the A or B or C gadget, which is this OR? Okay, so now the proof is trivial, right? So we get our proof, right? So somebody give you a 3-set formula that you get each clauses, right? So you can exchange each clause into OR gadget. And you just create the OR gadget or gadget, and let's change into OR gadget. Okay, and suppose you have M clauses, then you have M OR gadget. You have M of this graph diagram, and then now you can just connect the previous variable. Okay, so which you got a large graph, right? So you can construct a large graph G of phi. Okay, and the very intuition, it's very obviously that, so how obvious is if phi satisfiable, then by construction, right, you can prove that G phi is satisfiable. Sorry, G phi is 3-colorable. Okay, and the converse is also true. Okay, so if G is not satisfiable, then G phi is not 3-colorable. And the proof is trivial, right, because we already proved that for each OR gadget, if these small OR gadget is 3-colorable, then this is 1, right? If this graph is 3-colorable, that means that each small or subgraph is 3-colorable. So that means each gadget each clause is correct, is 1, then everything's 1. Okay, so very simple, right? Because if G phi is 3-colorable, then the subgraph is 3-colorable. Okay, so proof is also trivial, already done. Okay, by just construct the graph. Okay, and then this is polynomial. Reason is what? So this is polynomial. Reason is trivial, right? Because for each 3 gadgets, for each 3 variable, you exchange with this gadget. So this gadget is finite, right? You can see that this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? So you can just, for each small variable, then each 3 variables, you just create 13 nodes or 13 vertices. And for each for the original gadget variable, that suppose you add n variables, you get 2n plus 1, right? That previous, 2n plus 3 variable gadgets variable. Okay. So this is your total results, which is polynomial. If you have m clauses, then you may get like 13 m modes. If you get n variables, you get 2n plus n variables, right? So if m is a poly n, then your graph, the number of the vertices in the graph is actually poly n, because you just 2n plus 3 and 13m. Okay, so this is the most, I think the first difficult proof in my video that proves something is not be complete. Okay, so let me just create another small topic that I want to prove today, which is also very easy, is that the 4-colorable is be complete. Okay. Oh, by the way, so one should very easy to check that 3-colorable is NP, right? Because if somebody give you a graph which is 3-color, then you can just check edges, right? So you can just check edges. You check whether each edges the adjacent vertices has different colors. So this is simple, right? Because you at most have the order m, right, which is at most O squared for a simple graph. Okay, full colorable is NP complete, right? So very simple. Somebody give you a full colorable, however, right? You just check a edge. So it's full colorable is still in NP. But one can easily show that three colorable is a subset, is a polynomial reduction to full colorable. Okay, so proof. This is very simple, right? Somebody give you a graph G. Let's say I give you a graph G. Okay, maybe this is graph G, and I create another node. As I create a green node and connect each vertices with this green node. Okay, and I call this graph G prime. Okay, and my claim is that very trivial, right? If G prime is full colorable, if and only if G is a three colorable. Trivial, right? If you can use a different three colors to color G, then the G prime connect every of them. G prime must be you just add another color, right? So which G prime is full colorable? If G prime is full colorable, then the G must be three colorable, right? Because G this color must be all different from G. Okay, so proof is trivial. Okay, as I say, and one can keep going and say that five colorable isn't become really six colorable isn't become B, right? But actually the problem become simpler, right? If you increase the number of colors they can use. Okay, so you can view that three colorable, probably the difficult one. Okay, but yeah. Okay, so see you guys next videos. And the next video that I will prove that actually one can start from a three colorable and the reduction and get the independent set. Okay, once we get independent set, we get vertex cover, and the vertex cover will give you the integer linear programming. Okay, see you guys next videos.